Okay, so before we start the new topic today, let's just go over the things, some of the things which we discussed in the last lecture and where we ended. So, do you see the shared screen?
Yes.
Yes.
It's a bit small. I mean,
Yeah, I'm
Can you
trying
zoom
to enlarge it. Is this better?
yes.
Yes.
Okay. So, remember we saw how this these parameters which we defined in the context of descent sets of a permutation were revisited and we computed them using the determinant, right? So this anyway I corrected. I should upload the lecture so that it incorporates this particular change. And once you have seen this, I also said that there are different variants of this particular data which could be considered, right? So all those invariants can be generalized and captured in one particular result, which should have been stated and it got missed last time. So it says that if you have S, the set of properties to be given as P1, P2, Pn, and then T to be PS1, PS2, Psk be a subset of S. Okay, so you're considering some K properties of these N properties such that these K properties are arranged. So the set, you have a total ordering here. All right. Then if you assume that the F less than equal to T has the form Hn E S0 S1 E S1 S2 and so on till E Sk plus 1 for some functions H on the set of natural numbers, and these EIs are the functions on n cross n. Okay, with S0 as we had done in the last time also. Yeah, so S0 is always said to be 0. S of k plus 1 is said to be n. All right, and S1 up till Sk comes from here, the subset of property set. All right, so with this thing in picture and keeping E of ii to be 1, this is how we had defined even here. Fii was identity. And again, I think we got confused last time putting that this should have been an Si plus 1 minus Si.
Yes, ma'am.
So that is incorrect. What I said was wrong. What indeed it is that you take the determinant of the matrix whose ijth entry is given by this element.
Okay, ma'am. Yeah.
Okay, so there was no typo in this. I just got confused when we were doing it last time. So the ijth entry is actually given by, the elements which are involved are Si and Sj plus 1. So you take one entry up. And this is how you actually reach into the upper triangular sort of matrix.
Yes.
Okay, that is why all this here remains 0. And since f of ii was defined to be 1, so instead of ones at the main diagonal, they are here, shifted. And then these entries comes from these entries. Okay?
Yes, ma'am.
So with this notation, you just, if you remember this entire machinery with all these notations and how we came up till the point. So you see, this is nothing but determinant of the matrix formed by elements whose ijth entry is, instead of Fij, it is Fij plus 1, right? Because you're taking the reciprocal of Sj plus 1 minus Si factorial, which is Fij plus 1, correct?
Yes, ma'am.
So entries of this particular matrix whose determinant you are to take is f of I j plus 1. That gives its ijth entry, not ij plus 1th entry. So this is the point which I messed up last time. Okay.
Okay.
So in contrast to this, if you keep comparing these things, you can then see that this is the function which we tried to define here through this. Okay, so these E S0, S1, so EII is said to be identity and E of ij is said to be 0 whenever I is bigger than j. All right. And then, so this is a function which sort of took the form of f earlier. And now in the general setup, when you take any k properties out of n property set, this f equal to t, this number is given by the function hn, and then determinant of the k plus 1 by k plus 1 matrix formed by entries of E, Si, S, j plus 1. Just how we had here Fi, j plus 1. Okay? Is this fine?
Yes, ma'am.
So here we see how determinant comes into the picture even when we are trying to do this count of descent set. And today we will see after some time how, so here there is some particular structure to which we have, whose determinant we are taking, right? We are defining some EII to be 1 and other things to be 0, and then some non-zero entries pop up which are not given here. So you see here, E is defined not on the whole of n cross n, or even for that matter, k plus 1 cross k plus 1, right? Only on some portions it is defined to be 1 and 0. In the particular cases, we saw this particular case, the rest of the entries are given by 1 upon Sj minus Si factorial. Similarly, in different other cases, this E is defined for the rest of the entries, and that way you get the definition, you get this full matrix. In today's lecture, we will see for other types of determinants, what can we expect? Okay, combinatorially, what that gives. All right.
Yeah.
So then now let's start the new lecture. So is my screen visible now?
Yes.
What are you able
Yes.
to see?
Involution.
Involutions, right?
Yes.
Okay. So, okay. In your notes, you can also try to see what was equation 5. Okay, otherwise also we have it here. So last time it was all about trying to do the counting in 2 ways and then show that some equality holds, because that number or that entity is counting the same number. So only thing which happens is that you do the counting in 2 different ways, right? So that is what we are going to do even now. So we see how the principle of bijective proof can be applied to this particular equation, and then that will in short give us a combinatorial proof. So f equal to of empty set, in last time itself we have seen that this is given by alternating sum of the sets of f greater than equal to y. Okay, but as we said in the last lecture itself, whenever you're doing this counting, this really is not counting the cardinality of some set. It's a difference, right? It's a difference of some numbers. So to put it in the form which we can deal, we put the elements here which are coming with a negative sign to this side of the equality, so that then both the sides will only have summations. Okay. So rewriting with all positive signs on both the sides, what you finally get is this. So f equal to phi plus f greater than equal to y with cardinality of y odd. Why cardinality of y odd comes here? Because that is what gives you the negative sign here, right?
Yeah.
Yes.
Yes. Yes.
Okay.
Yeah. So here,
One. Okay. So this summation is equal to this summation, and if you want to prove it, let's just go ahead with the combinatorial way which we have learned, which is that you do the counting of this, you do the counting of this, and show them that they turn out to be the same.
So for 3 micron
Okay.
stabilizer, next week.
So if you let
the guy
M
from
to be
TM,
the set
they
of
would be
elements
probably ready to do
that
the
have
meeting.
no property
So
of
he
S,
suggested, the day I was traveling, that
which
day he
means this.
suggested, but then since I was traveling, he could not do it. So I have suggested him.
Ma'am, are you saying something? I can't hear you.
Sorry, this thing was on mute. So I said that once you have put this equality, I am putting this number to be equal to cardinality of some set, this to be cardinality of some set, and this to be cardinality of some set, right? So this clearly is the set M with, so if this is some set, cardinality of some set M, then M is the set which has all those elements of A which do not have any property of S. Recall from last lecture, A was the set of objects and S was the set of properties, right?
Yeah.
Remember that? So M is the set of all those elements that have no property of S. N is this cardinality, N's cardinality is this. So N is the set of all those objects which have properties which are in Y at least. and the y should be of odd size. Okay, this set, this description is equivalent to saying that N is the collection of triples x, y, z such that x belongs to A, has exactly the properties of y, where y is some superset of, properties z, and z is a superset of y with y's cardinality being odd. You see this? So what you're doing over the y, you're seeing all the bigger sets that contain y, all right? And then once you have collected all those sets, you can say that it's nothing. So this set then is equal to, is f equal to of z when mod y is odd, right? And you will have to take union over all such z. That is the collection N. Understood?
Yes.
Yes.
Okay. And just how you would do this for y odd, similarly, you can do this for y even, where it says that you collect all the triples x prime, y, z prime, such that x prime is in A. Okay, so some prime is missing here. So x prime is in A. It has exactly the properties that are there in y, z prime. Z prime contains y, and the cardinality of y is even, right? So if you put a total order on the set of properties and define this function sigma from m union n to n prime as follows. So m has elements of this type, n has elements of this type, and n prime has elements of this type. So first of all, if you deal with this kind of an element, so x should go to something in n prime. So what is this n prime? N prime has the cardinality of y to be even, and z prime should contain y. So if you're really trying to define a bijection, see why you're trying to define this? Because we wanted to show that this quantity is same as this quantity, correct? So if you can put up a bijection between this set union this set and this set, then you are done. Because their cardinalities are exactly the elements which are there in your equation. Isn't that so?
Yes.
So to prove this identity, we are trying to define this function from m union n to n prime, and we will claim that this is a bijection. Okay, so firstly, if you deal with elements in M, then any such element X should be sent to X empty empty. Is this part clear? So X empty empty. So first of all, this is where your Y coordinate comes in your N prime. So the cardinality of Y is, for empty set, 0. And Z prime also is empty. So cardinality of Z prime is also 0. So it matches up with the notation here. It can be sent. Is it well defined? Yes, people?
Yes. Yes.
Okay. So we are good on the elements of M. Now coming to the elements of N. Elements of N can be divided in two ways, in two subsections in some way. So what you do first of all is that, first observe that we have put a total order on S. right? And S was the set of properties, which means the properties are sort of arranged in, let's say, P1, P2, Pn manner. Okay, then Y is some subset of P1, P2, Pn, and Z is another subset of P1, P2, Pn, provided that Z contains Y, right? So then both of these sets, since they are subsets of totally ordered sets, they are also totally ordered, Y and Z, right?
Yes, ma'am.
And they are finite sets because the set of properties was finite. So in particular, they are bounded from below. So do they have a least element?
Yes.
Okay. So Y and Z both have a least element. But when Z is a superset of Y, what can you say about their least elements? So if you take the least element of Y and you take the least element of Z, how are they related?
Least element of Z will be less than or equal to least element of Y.
Great. So with the less than equal to equation there, you have two possibilities. Either it is strictly lesser or they are same, right?
Yes.
So that is how we define this function on the elements of n. So you start with an element x, y, z of n. So this triple is an element in n. And now you compare their least elements. So since you're dealing with finite sets, I can write as well min. So if min of y happens to be min of z, which is, let's say, I. Okay, so I is some property now, right?
Yes.
So when the min happens to be the same, you take this min off from your set y. And remember, the elements that are there in n, for these, the cardinality of y is odd. Here, you see? Okay, so when you have done the removal of one element from y, the cardinality of y has changed its parity. So from odd, it has gone to even. Yeah.
Yes.
Yes.
And y was already a subset of z because here itself it was true. Now you have taken one element off from it. So y minus I is still a subset of z. So x, y minus I, comma z is a triple in n prime. Is that right? N prime was this. So it has exactly the property z prime with cardinality of y being even. So you took the same z prime. Z is z here. Okay. So this element x has the property exactly which are there in Z. This Z contains this particular set and the cardinality of this set being even. So are we good so far?
Yes.
Great. Now, dealing with the next condition that the least elements of the property set Y and property set Z are not same, in which case the min element of Z will be strictly smaller than the min element of Y. Correct?
Yes.
In such a case, you put this element in your Y. First of all, if they are differing, it is clear that I is not in the set Y. That is why it's not the min element. Correct? So Y union I has a cardinality strictly bigger than the cardinality of Y. which
Yes.
means now y union I has cardinality different from the cardinality of y. Earlier y has cardinality odd, so now it becomes even. So x, y union I comma z is again a triple in n prime. Therefore, what you have defined here, these elements are indeed elements of n prime. So it's a well-defined function. Okay. Moreover, if you see this new function, which takes any triple x, y, z of n prime and send it to x in M, if y and z are both empty, it sends it to the triple x, y minus I, comma z. If y was not empty and the min of y and min of z were same, and to the element x, y union I, comma z, if z was non-empty and the min of z was strictly smaller than min of y. If y happens to be empty, you set the minimum of y to be infinity. Then both these elements are in M. Here y, if you're seeing this y has to have a cardinality even because it's an element, this triple is an element in n prime, right? So again, as soon as you have an element in n prime with y and z as being finite subsets of a totally ordered set, again, you can look at their minimum elements, and minimum elements of these two sets could either differ or be same. If they happen to be same, which is this case, you take the element off from the set which is smaller, okay? So that now for this, the cardinality has changed, it has reduced by 1. And for this particular set now, the min of this set is strictly smaller than min of this set. So sorry, the other way around. Min of this set, min of z is strictly smaller than min of y minus I. Correct?
Yes.
Are you people able to see the contrast? I mean, how this definition is actually working?
Yes.
So this really corresponds to this. When you had added an element, you landed here. When you remove an element, you land here. Right? By putting this element here, you make their least element to be same. Okay. So when you have same elements, you just take this off and then you're back to x, y, z. Right? After the I has been deleted from here. Correct? And vice
Yes.
versa. So clearly this sigma inverse, I should not have written sigma inverse as of now, but this particular function which is defined in this fashion defines a inverse of the function sigma which we defined here. Therefore, the sigma is a bijection from M union N to N prime. And therefore, this equality holds. All right. So fine.
Yes.
Okay. Now moving further, let's see what really happened here. So in the definition of sigma prime, sigma inverse, if we identify every element x in M with x empty set of n prime, so that then you can actually write sigma inverse of x empty to be x empty instead of x in M as we did here. Then the function tau, which you set as sigma union sigma prime, sigma inverse. So now this is a function from n union n prime to n union n prime, right? So these elements are taken off from the set of elements which we dealt with here. So here there were exactly 3 sets, m, n, and n prime. Okay, there were some sets which were not so important to us, or in short, which sort of, kept the elements of m to itself. N went to n prime and n prime came back to n. But m stayed to itself. So that is not interesting for us. You want to see what happens to the elements in n union n prime. So if you take the sigma union sigma inverse from the n union n prime to n union n prime, call this as your tau, then this is a function which satisfies the following properties. So tau, when applied twice on element of this, comes back to the same element, which means tau square is identity. Okay, such a function which satisfies this is called an involution. So this is what I was trying to show you here when we said that observe that this element goes to this, and when you remove, so start from x, y, z. Okay, remember or keep a note of this fact to yourself that minimum of z is strictly smaller than minimum of y, and that is why you are adding the element y here. After you have added the element y here, if you treat this y union I as some y prime, okay, then in the x y prime z pair or triple, sorry, you have that their minimum elements are same, correct? So when the minimum elements are same, according to this definition, I take the minimum element out from the set y, which is y prime actually. So this is my y prime. So this particular y is this y prime. Okay. So from this y prime, you remove this y. So y prime was this y union I, and from this, you are then doing a minus I. Okay, so what you're really left with is x, y, z. Same thing which we started off with. Right?
Yes.
And similarly, if you consider the other one, so when you consider this, let's say, so when you have started with x, y minus I and z, and now this you treat as y prime, y minus I is treated as y prime. So here once you have taken your y out from this set, the minimum of this set now is bigger than minimum of this set. Correct? And with such a scenario, clearly when the minimum is different, then Z is automatically non-empty. So for non-empty Z, the definition of the inverse says that if their mins are different and Z is non-empty, you put I back in your Y.
Do you think taking a thermal image would be helpful?
So here in the Y prime, Y prime now has your I in it.
No conclusion
you take
from that, or?
Sorry, Y prime has I removed from it. So here you are putting your I back, and what you get is what you started with, which will be Y. Correct? So here this is actually your y prime. So from y minus I, you do y prime and then y prime union I. So it's a y minus I union I. So ultimately what you are left with is x, y, z, right?
Yes, ma'am.
So no matter which element you attack on, if you apply the same function twice, what you're left with is the element you started with. Such functions are called involutions. And fixed points of tau are the triples x, empty, empty, which means they go to themselves because you have already identified them, right? So in effect, what you know is that elements of n union n prime go to each other. Elements of m go to elements of m. And so that what tells you further is that fixed points of this tau are in one-to-one correspondence with m, which means the number of fixed points of tau is exactly the cardinality of the set m, right? So if x, y, z is not a fixed point of tau, and we set tau of x, y, z to be x, y prime, z prime, then -1 raised to cardinality of y plus -1 raised to cardinality of y prime is 0, right? Because this goes to itself, and then when you would apply tau here, you will come back to this. So they sort of cancel out with each other. Okay. Thus, what involution really does is that it selects terms from the right-hand side of this equation. Okay, here, sorry. From here, it takes the terms, add them here, and then the irrelevant terms gets cancelled out, and what you're left is the answer. Okay, so involution selects terms from the right-hand side of 2.5, add them up to the left-hand side, and then tau cancels out the remaining terms due to this. So this involution is taking place and the in pairs terms gets cancelled out. More generally, every set you can sort of partition into two, x plus and x minus, called the positive part of x and negative part of x. So it's a disjoint union. You see, instead of a cup, I have used a square cup. Okay. So if you assume that tau b is some involution on x that satisfies that tau of x is y whenever x is not equal to y, then the cardinality of this set intersection x plus is 1. What does this say? If tau of x is y, then both x and y cannot be in x plus. In fact, it says more. What is that says? Both x and y cannot be in x minus either. So this intersection is exactly one element, either be it x or be it y. And since x is x plus disjoint union x minus and tau is an involution on x, so if one of the element is in x plus, the other element automatically is in x minus. Okay?
Yes.
And if tau of y is y, which means if tau is a fixed point, then it is necessarily in x plus. So these are the two properties that you demand some involution to satisfy. Okay, so these were the properties which were being satisfied earlier in our setup. where M was the set of fixed points. So M had these points. So X plus was actually M union N. Okay. And N prime was your X minus. You see this? So all the elements that appear here, all the elements that contribute to this or this or this, every element can contribute to exactly one of these, every element of A. Isn't that so?
Yes.
You cannot you cannot have some element of A which does not satisfy any property of the set S and at the same time satisfies some properties, at least the properties of the set Y. Similarly, you cannot have that it satisfies the properties of Y where Y is cardinality odd and cardinality even. Does not make sense, right? So every element of A either corresponds to this sum or this sum or this sum. So the set A here is actually defined, it's divided into three parts. This part on the left-hand side is the X plus, which contains the set of fixed points and the other points. And this is the set of minus part of the set, which is X minus. And it contains exactly the ones which it convolutes with, the elements. These elements remains fixed. They stay to themselves. Elements of here go to here, elements of here come to here. Okay. So this is the setup which we are trying to define in general now. So yeah. So if you define the weight function W on X as W by X to be 1 if X is in the positive part and minus 1 if X is in the negative part of X, then the cardinality of, so fixed tau means set of fixed points of tau, and then this hash here means cardinality of this set. So then the number of fixed points of tau is nothing but the summation running over all elements of X and you sum their weights. Is that right? Because the weight is plus 1 if it is in X plus, it's minus 1 if X is in X minus. So using this part, you know that if something is here, it's sort of its pair is in the other part. So if small x happens to be in X plus, automatically Y goes in X minus. So if this comes with a weight plus 1, its image will have a weight minus 1. All right. So elements of X minus will have a total of weight minus 1 times cardinality of X minus, and that much gets subtracted from the cardinality of X plus. So once you have taken out as much part of this from here, then whatever is left here is exactly the fixed point set of this involution. So that is the number you have here. Correct? So you see again how this cancelling business happened. So this particular tau, which you were saying as involution, it selected terms from the right hand side, okay, which really adds up to the left hand side. And then cancelled out the remaining terms. So Wx is actually the cardinality of entire X plus minus the cardinality of X minus. You see what is happening?
Yes.
Ridwan, is this clear?
Yes, ma'am.
Okay. So if you assume that all of the above that holds for X to hold for another set X tilde now. Okay, so as before, X tilde is also divided in, it's partitioned into its positive and negative part, and it comes with an involution, let's say tau tilde. And you have a sign preserving bijection between these two sets, which means that the plus part of X goes to the plus part of X tilde, and the minus part of, or rather negative part of X goes to negative part of X tilde. Then the number of fixed points of tau and the number of fixed points of tau tilde are same. This is what you would expect, right? When you already have a bijection which is preserving the negative and positive parts of your sets X into X tilde, then the fixed points of tau and fixed points of tau tilde should be having the same cardinality. So let's just see a proof of this. So to prove this, again, we'll do the same way. We'll try to set up a bijection between these two sets. And then once you know that it's a bijection, automatically you know that the cardinality of this set is same as the cardinality of this set, right? Right? I can't hear anyone.
Yes, ma'am.
Yes, ma'am.
Okay. So to construct this bijection between these two sets, we are going to do this into a very canonical way. And this particular way of constructing such a bijection is called an involution principle. So what it really does is that you start with a fixed point of tau, and then, as obvious it may sound, you have to send it to some fixed point of tau tilde, right? Which fixed point should it be sent to is what you have to figure out, right? So now there are few maps in my hand. First of all, I know that F is a bijection between X and X tilde, which preserves these parts. So as soon as you know that F is a bijection, you know that its inverse is also existing. Okay. So starting with a fixed point of tau, you look at the element which is given by this. So you take f of x lands in X tilde, then you apply tau tilde. So since so X is in the fixed point of tau, in particular, X belongs to X plus, then f of X will belong to X tilde plus because F was sign preserving. Okay. And then tau tilde being an involution will keep the elements of, so if you remember here, tau of y is y, then y belongs to X plus, I know. But if y is in X plus, I am not sure if it goes to a different element, which would be an element in X minus, or it comes back to the same one, right? So tau tilde will send fx to either itself or something in X tilde minus. So far with me?
Yes.
And then you apply inverse to it. So you come back into the set X. Now, depending on what tau tilde would have done to the element Fx, F inverse of that element is going to be either in X plus or in X minus, right?
Yes.
So this complete iteration you keep on doing until the element what you're left with when applied to F, when F is applied to that element, you are landing in the fixed point set of tau tilde. Since the X is finite, this iteration has to stop. It's going to be like a cycle going round and round and round, and ultimately it has to come back to its initial point in some sense. Correct? So
Yes.
the first time it hits the fixed point set, that is how you define your function gx. So gx is defined to be the f of this entire function applied on x, where n is the smallest non-negative integer such that this is into the fixed point set of tau tilde. Okay, check that this way of defining G on the set fixed tau is a bijection. And then we are done, right? Once I will show visually what it is giving us, and then it is obvious, pretty much obvious. So this entire huge, humongous looking thing is simplified visually by taking this diagram. So in this, what I have done, I have considered some elements here. First of all, I know that there is a bijection between x and x tilde. So on my left, I have x. On my right, it's x tilde. Right? So as soon as you know there's a bijection, the elements of x and x tilde are same. So this goes to itself, this one. This goes to this one. So this sort of parallel edges I can draw. Okay. So starting with the set x and x tilde, you start constructing a graph now. In the graph, what are your vertices? Vertices are the elements of x and x tilde. So these circles which you see, hollow circles, these are my vertices. Now you put all the edges given by the function f. Okay, so these are those edges. Further, you put the edges which are given by involutions. So there are involutions which act here, and there is an involution which act here. Okay, so for this involution, it sends this element of x plus to this element of x plus, x minus. This element goes to this one goes to this one. A goes to itself, therefore there is no edge. B goes to itself, therefore there is no edge, which you see here, which means A and B are fixed points of the involution on x, which is tau. Okay, similarly for x tilde, you have a x tilde plus x tilde minus. Don't look at these sides as of now, but what you do is the same thing here. You draw the edges given by the involution on x tilde, which is the tilde tau. Sorry, tau tilde. Okay, so it sends this element to here. See how carefully this is really drawn. So this element is an x plus of tilde, and this is an x minus of tilde. Similarly, this is an x minus of tilde. It is going to this element. This goes to this element, and this goes to this element. This element goes to itself. This element goes to itself by the tau tilde. Okay. So this way we have drawn all the edges in this diagram. Now, When I start with a fixed point of x, let's say a, then it goes to something in x tilde. I come there. Now I see where the involution takes it. Okay. So involution would either have not done anything to it, in which case I stop here, right? Because if involution keeps it fixed, then the image already is in the fixed point set of tau tilde. And then when you would have applied your F inverse, you're going to hit back the same element and then you apply tau. And since it was in the fixed point set, you stay here. So this entire business is actually n equal to 1. Correct? So we were discussing what happens if you started with a fixed point. So if I start with a fixed point, I come to something in the x tilde plus for sure, that I know, because fixed points are elements in the x plus. And since the function f, which is a sign preserving bijection, has to take elements of x plus to x tilde plus, therefore these elements have to be part of x tilde plus. Okay. Now after involution, they either stay in the x plus, which means they are fixed points, or they go to x minus. Guys, these are the only two possibilities. So if they stay in the x plus, which means it was a fixed point, that case we just discussed. Second case is it goes to x minus. So this point goes to x minus. So you come here. Now, once you're in x minus, you take the F inverse, which is going to take element of x tilde minus to an element of x minus. So you come here. Now, elements of x minus are certainly sent to elements of x plus by involution. That we know, correct? So this element goes to some different element here under tau. And this element is in x plus now. Now, on this element, you see what f does. If it sends to a fixed point, which is the case here, then you define this to be the value for this particular input. Okay. With me so far?
Yes.
So this happened when the element of fixed point was chosen. So fixed point went to something, it went to other part, you extract it back in the same part, then you apply the involution, you go to the different part. See, it's very clear. If here itself in the involution, it did not change part, that means you're already hitting a fixed point. Right?
Yes.
So for every such thing, so fixed points start with something either in the first direction itself, you hit a fixed point for it, or you change these parts from negative to positive, positive to negative until you hit a element in the same part and which is going to be a fixed point. So the first time you hit the fixed point is how you define your function g here. Sorry, where is this going? This is what it is saying. First time you hit the fixed point of tau tilde, that is what you define your gx to be. Okay. Otherwise, what really happens, you see, if you're, so that gives me a bijection Why is it a bijection? So for reasoning that, what I should say that the other elements in some sense cancel out. And what does that mean for the other elements to cancel out? Is that if you start with some element which is not a fixed point, okay, so when you apply your bijection, so if it is not a fixed point, it could be either in x plus or in x minus. Let's say I start with an element of x plus first. So this element you start with the x plus. Remember, this is not a fixed point now. You apply your f. If it was an x plus, it goes into x tilde plus. You come here. This was not a fixed point. This is an x plus. You apply involution. You change the part for sure. Why do you change the part for sure? Because what you started with was not a fixed point. Okay. So this is also not a fixed point. You come here, and once you're here, you have already changed the part. You take the F inverse, you come in the same part of the domain, and then you again apply your involution, and it is going to change the part. And if you started with x minus, then anyway, involution is going to send the elements to x plus. Okay, so something here has to go here, something here has to go here. And here it just shows 1 4 cycle. But depending on how many elements are there, I mean, I have drawn a very small example, actually from the book as it is. But if you have many more elements here, you could have a large cycle where this will keep on going like this. So something will start here, come here, go to something here, let's say then go to here, then that will come here and that would go here and so on. Okay, but the main point is that if you do not have you have not started with an element of fixed point of tau, you keep on moving and this ends into a cycle. Okay, so to sum this up, what we are really doing is that if you treat the elements of x and x tilde as vertices of a graph gamma, and two vertices of this graph are adjacent, if both happen to be in x and tau of x is y, okay? So here you are seeing the involution edges, and here you see the edges of f. That is what I've written here. So x, y, and x, then tau x equal to y gives an edge between x and y. X, y both in x tilde, and tau tilde of x is y. That is the edges on this side, the curved edges here. Or one of the elements is in x, another one is in x tilde, and f of x is y. Okay, these are these horizontal edges, which we first drew. Then clearly every component, connected component, if you see of this particular graph, not tau, this is gamma. So this is gamma, is either a cycle which does not intersect the fixed points of tau and tau tilde, or you have a path which will start with a fixed point in tau and end in a fixed point of tau tilde, like we saw here. So started with a fixed point of x plus, which is a fixed point of tau, okay? And you went on in circle, circle, circle until you ended in a fixed point of tau tilde, okay? So these vertices, the other vertices in this path would never intersect with the cycles which would appear when you have started with an element which is not a fixed point, which I just explained, okay? So either you have a cycle which does not intersect fixed points of tau and tau tilde, or it is a path which starts, whose one endpoint is in fixed point of tau tilde, tau, and other endpoint is in fixed point of tau tilde. So if the first endpoint, the endpoint in tau is say z, and the endpoint in tau tilde is z tilde, then you define g of z to be z tilde. And this is precisely what is being captured through this pictorially. Okay. So with this, we have finished the involutions. Just to mention, there are many variants of this particular data. So just here how we have taken, we started with some particular set X having two parts, and then we slowly progress to saying that, oh, what happens if you have another set with such a property, and if there is a bijection between X and X tilde which preserves their parts. And you figured out that there is a bijection between the fixed points of tau and fixed points of tau tilde. Now you can ask a even more difficult question, which is that you start with X and X tilde, and now they are also disjoint finite sets. Y is some subset of X, Y tilde is some subset of X tilde, and you have bijections between X, X tilde, G being a bijection between Y and Y tilde. Now, following the similar sort of construction, can you construct a bijection between X minus Y and X tilde minus Y tilde? At least this is clear that once you have this as a bijection and this as a bijection, then X minus Y has same cardinality as X tilde minus Y tilde. Right?
Yes.
So these two sets have the same cardinality. What it is really asking, the new variant, is that you should try to define a canonical bijection between these two sets. So it's there in the book. If you're interested, you can read it up. For us, this is enough. And now let's proceed to the next topic, which is determinants. So remember when we started this lecture, I said that we have seen how determinants appear while we tried counting the parameter beta for the descent set.
Yes.
Right? So there we had considered a specific type of determinants. Here we'll try to see a little general setup. So okay, so earlier what we dealt with was the case when you took the determinant of the matrix Aij, whose ijth entry was 0 whenever I minus 1 was less than j. Why all of a sudden I minus 1 less than j? Earlier we took I less than j, right?
Yes.
Yeah, so is this a typo or is this fine? Yeah. See, remember earlier when we did this, we actually took determinant of a matrix Aij, where Aij were special in the sense that the entries were not Aij but Aij plus 1. The entries were given by
Yes.
Fij plus 1. Correct? So to keep that index same in the way here, now it is Aij for I minus 1 less than j, or equivalently I less than j plus 1. Remember, ijth entry was such that it was given by Fij plus 1. And Fij plus 1 had the property that whenever I was less than j, it was 0. I was bigger than j, it was 0. Bigger, I think this, I have made a mistake again. I minus. Yeah, it should be bigger, not smaller. That's the typo. Okay. Okay, you understood what I'm saying? This is reverse inequality. It's this. So we saw how this was interpreted combinatorially last time using the principle of inclusion and exclusion. Now we will see arbitrary determinants and their significance. Okay, so first let us quickly recall lattices, though we are going to deal with this in much more detail in our next unit. But for now, let's see what is a lattice. So a lattice path L in z raised to d of length k with steps in a set S. So now this set S is a subset of z raised to d. It's a sequence of points v0, v1, vk of zd such that each consecutive difference, that is vi minus 1. So when you take this subtraction in the sense of component wise, then this is also an element of zd. Right?
Yes.
So this difference is, if this is an element of S, for every consecutive points here, then you call this as a lattice path. Okay, length k means there are exactly k plus 1 points. So there are exactly k differences. For example, if you take d to be 2, so I'm going to work just in z2, z square, and S to be the set 1, 2, 1, 2 intersection z2. So many people actually write this to mean that they are considering the set 1, 2, 1, 2. But just to make it consistent in the sense of this looks like a closed interval 1, 2 as well, right? So this intersection with z2 then just leaves me 1, 2, 1, 2 cross 1, 2, right? So you'll have 4 points 1, 1, 1, 2, 2, 1, 2, 2. Correct? So here I have drawn lattice paths from the point 1, 1 to 2, 2. So you have, and these lattice paths I have drawn in Z2 with steps 1, 0 or 0, 1. So 1, 0 means the difference is a 1, 0, and 0, 1 means this difference is a 0, 1, which means this difference is either a 1, 0 or a 0, 1. This difference being 1, 0 means what? You're actually moving in a horizontal way from left to right. Right? So this is some AB, this is some CD. So you are saying A minus C is 1, B minus D is 0. B and D are giving the y coordinates. So there is no change in the y coordinates, and the x coordinates, there is a change of 1, which means when you're standing at some point, you're moving in the direction from left to right horizontally. That is a step 1, 0. Step 0, 1 similarly means you are going from bottom to top. Okay, which means you are with steps this and this means only allowed points in this sequence are, if you're standing at V0, you could either go a right from V0 or you could go a up from V0 and you arrive at V1. Similarly, at V1, you could only go a right or you can go a up. Okay. So with this, there are exactly two lattice paths from the point 1, 1 to 2, 2. First is that you go from 1, 1 to 2, 1, 2, 1 to 2, 2. So you have taken a right first and then a up. Or you would have taken a up first and then a right. Is there any other lattice path from the point 1, 1 to 2, 2? Yeah.
No, those are the
Aglan?
I also think.
Okay. So this is an example for a lattice. So things to remember for a lattice. First of all, you need to know which space you're working in, what are your steps, and what is the set S. Okay. So in this particular section for the determinants, what we are going to do is that we are consider lattice paths in n square with steps 1, 0 or 0 minus 1. Okay, so 1, 0 we have already seen means right, going right, and 0 minus 1 is contrary, like it's exactly opposite of 0, 1. So 0, 1 was going up, which means 0 minus 1 is going down. Okay, so we'll consider lattice paths which have steps going either right or down. Okay, now some terminology, so just stick with it. An n path is an n double L, so this is calligraphic L and not alpha. So calligraphic L is equal to L1, L2, Ln of n many lattice paths. So each of this is a lattice path, L1, L2, Ln. So for instance, let's say this is L1, this is L2, and so on. So you have n many such lattice paths. You put them up together and you call it a n path. Okay? N path is an n tuple of n lattice paths. And now you take these vectors in n raised to n. Each vector is having n coordinates. Okay, alpha, beta, gamma, delta. Then the n path L is of type alpha, beta, gamma, delta if the lattice Li goes from beta I, delta I to alpha I, beta I, gamma I to alpha I, delta I. Okay, in between, outside, outside. Simpler way to remember. Fine. So
Yes.
can you tell me what is L1 going from? What is the lattice L1?
beta 1, gamma 1 to alpha 1, delta 1.
So these points you're collecting from here. Okay. So even though these elements look like they are in n raised to n, all of these lattices are living in n raised to 2. Correct? Because beta I is a natural number. Delta I, gamma I is a natural number. Alpha I is a natural number. Delta I is a natural number. They're coming from here. So beta I, gamma I. This is one point in n raised to 2. And then from that particular point, you have to go till alpha I, delta I, which is another point in n raised to 2. Okay, so that is the lattice Li. Like this, you will have n lattices. And together, these n lattices form an n path. Okay. So you will call an n path L to be intersecting if for some distinct I and j, the two lattices intersect. Okay. So here, if I have taken this and this to be my lattices, then certainly they intersect. Where? Here and here. Correct? 1, 1 and 2, 2 are common points to both the lattices. Right?
Yes.
However, depending on what I choose my alpha, beta, gamma, delta, I may have lattices which do not intersect. In such a case, if none of these lattices intersect with each other, I would call the n path L to be non-intersecting. Okay. Now, on the horizontal steps, we can put weight. So how do we put the weight? When you go from the step ij to I plus 1j, first of all, this should be clear that when you're taking a horizontal step, this is the only way you could have gone. Ij to I plus 1j, right? You have to go right. So I has to shift to I plus 1 and j should not change. Correct? That is how it's a horizontal step. So weight on a horizontal step from this to this is the indeterminate xj, because j is the only thing which is fixed here. Then weight gamma of L is defined to be the product of weights of its horizontal steps. So here, if you come, what will be the weight of this step? Yeah. For every horizontal step of this form, the weight is the indeterminate xj. So what is this step? It is 1, 1, 2, 1. So what is the weight of this horizontal step?
X1.
Sorry?
X1.
X1. What is the weight of this horizontal step?
X2.
Right. And if there were, let's say, instead of 2, 2, I ended at 3, 2, and I had another horizontal step here, then what would have been the weight of this entire lattice? Yeah. It is the product of weights of its horizontal steps.
X2
So
square. X2 square.
x2 square. That's right. If you had another, let's say like this, then the weight would have been
X2 square times X3.
x2 square times x3. And if I had, let's say something like this, what would have been the weight?
X2 times X3 square times X4.
That's right. So you people understand what is happening, right? Okay.
Yes.
Now moving further. So this you have already understood. Now, if you start with a n-length vector alpha and you take a permutation of n elements w, Then let W applied on alpha in the most obvious way to be that you permute the elements of alpha through the permutation W or omega, whatever you want to call it. Okay, so alpha 1 is now actually changed to alpha of omega 1 and so on. So omega of alpha is this new n element set of n raised to n. It is this new n tuple. Okay. Now, there is some machinery which actually is not needed for the setup, but I thought it is better if I at least explain this, and then when you read the proof, you'll be able to understand the things better. So the calligraphic A, which is depending on the variables alpha, beta, gamma, delta, be the set of all n parts of the type alpha, beta, delta, gamma, delta. Remember the n path of type this means Li is a lattice which starts from beta I, gamma I to alpha I, delta I. Okay, that is when a lattice, that is when an n path is called of type alpha, beta, gamma, delta. Okay, remember this?
Yes.
Great. So if calligraphic A collects all the n parts of the type alpha, beta, gamma, delta, and A is the sum of their weights, then we consider a path from beta I, gamma I to alpha I, delta I. Okay, so this is actually a lattice. You are actually considering the ith lattice, correct? So if you consider this particular lattice or a path, I think we said also a lattice path. Okay, so it is interchangeably used. When you just say a lattice path, it's a single lattice. And when you say n path, it's a collection of n many lattices. All right.
Okay.
So when you have considered this particular lattice, you put m to be alpha I minus beta I. So why is m positive? Can someone quickly see and tell me?
Alpha was larger than beta.
Why?
The paths are like increasing, going from
Because the steps, allowed steps in the horizontal direction are moving
increasing.
right. Okay. So alpha I is always greater than equal to beta I. And since you're dealing with the non-redundant lattices, alpha is strictly bigger than beta I, delta I is strictly bigger than gamma I. Okay, so now if you consider any j which is in between 1 and m, then there is a unique horizontal step which looks like it is j minus 1 plus beta I comma kj, and it goes to j plus beta I comma kj, right?
Right.
So depending on which step you're standing at, basically.
Yes.
If there is a difference of m between alpha I and beta I, you will have to take exactly m steps in this lattice, m horizontal steps, right?
Yes.
And therefore, for each such horizontal step, you just put it down in words, which means this unique horizontal step is this. So now, but depending on which, at which height this step is, this is a horizontal step. But now this could have been, so like this in this example also, this is a horizontal step. So is this, okay? Both are coming for lattices going from 1, 1 to 2, 2. But this horizontal step could have occurred here or it could have occurred here, right? Therefore, you have two choices. Why these two choices came? Because the difference between this element and this element, there is a gap of 2. Either it could have been at the 1 level or it could have been at the level 2. So, keeping that thing in mind, what you do is that what space you have here, you can choose K1, K2, Km arbitrarily, right? So the vertical gap tells you how many possible ways, in how many ways this horizontal step could have occurred. And therefore, depending on this K1, K2, Km sequence, which lies between delta I and gamma I, you define the function h. Why we are dealing with this h all of a sudden? Not all of a sudden. This is what we, not here, but if you remember the is this visible?
Yes.
So f equal to of t was given by h of n for some function n, remember? So this is the kind of function which we are trying to figure out in the general setup. And of course, these entries in the matrix whose determinant is to be determined. Okay. So you say that you choose K1, K2, Km arbitrarily if delta I is greater than equal to K1, which is greater than equal to K2, and so on, greater than equal to Km, greater than equal to delta I. And therefore, we define h of m depending on the delta gamma I delta I to be the summation of h K1, K2, Km, x K1, K2, Km, and this summation now will run over all possible sequences that appear in this inequality. Okay.
Like which screen are you referring to?
Oh, sorry. Oh, is this visible now?
Yes.
So this HM we are defining for the delta gamma I delta I to be the summation of this product x K1, K2, Km, where the summation runs over all integer sequences which are given by this equation. Okay.
Yes, ma'am.
So the number of the A, which was the sum of their weights, is then given by the product of these functions h, and now m is, remember here to develop this theory, m was the difference between alpha I and beta I, but there is a alpha 1, alpha 2, alpha n, there is a beta 1, beta 2, beta n. So you have to do this entire business for each of these differences. So you take the product of all of these functions HMs, where m varies from 1 to n. So I've directly written alpha I, beta I, gamma I, delta I, and now this difference runs from 1 to n. Okay?
Yes.
So this m was taking care of alpha I, beta I. Now you take some other, let's say M2, which is going to take care of alpha 2 minus beta 2, and you have to do the entire business. And now you let calligraphic B to be the parameter depending on alpha, beta, gamma, delta, which is the set of all non-intersecting n paths of type alpha, beta, gamma, delta. Here it was the collection of all the n paths. Okay, this math cal A was a collection of all n paths of this type. Now math cal B is the collection of all non-intersecting n paths of this type. And then, just similar to what we did earlier, B is the sum of their weights. Then the theorem tells us, so we'll see the example in a moment, but before that, so theorem tells us that if alpha, beta, gamma, delta are elements of n square, such that for any omega in the Gn, the cal B of omega alpha, beta, gamma, omega delta is empty. Unless omega is the identity permutation, then the sum of their weights is given by the determinant of matrix whose entries are given by h of alpha j minus beta I, delta I, gamma I, delta j. This n 1 by n cross 1 by n matrix, where we set this to be 0 whenever there are no sequences in this equation. Okay, so if this does not hold true for k1, k2, km, if there are no sequences which fit into this, then you put the corresponding hi's, the function corresponding to that h to be 0, and you construct this particular matrix, and its determinant is going to give you the weight of the lattice, weight of the n path lattice of the type alpha, beta, gamma, delta with non-intersecting lattices. Okay, just to see a small example of this. So I have drawn here this lattice. So I have taken, okay, I should not have written like this, but what I was more interested in that, you consider lattices from points 1, 2 to 2, 1. Okay, this is one lattice, and another lattice you consider from point 1, 3 to 3, 0. So this you see is 1, 2, this is 2, 1, this is 1, 3, and this is 3, 0. So from this point to this point you consider lattices, from this point to this point you consider lattices. There are going to be several lattices. Okay, now when I'm dealing with this math cal B, I have to consider only the non-intersecting lattices. So if let's say I draw a lattice, if I construct the lattice from this point to this point to be this, then there is exactly one lattice choice available for the point from this to this, which is going to be this, right?
So, so in the horizontal direction, we should only increase, right?
Yeah, you can only go right. You can go right and you can go bottom, as in down.
Yeah, okay.
So these are the steps which are fixed. You go right or you go down. You cannot go any other way. Okay, and these points are in a sequence. So it's not like, oh, I started from the rightmost point and then I started moving towards the left. No, that's not allowed. V0 is given to be the initial point and Vk is given to be the final point, and at each of these points you have to follow the rules of right and down. Okay.
Okay.
So
Yeah.
this is my V0, this is my Vk for the first choice of lattice. This is my V0 and this is my Vk for the second choice of lattice. So I have to actually consider Cal L, Math Cal L with L1, L2, possible L1, L2s. And then what are the possible L1, L2s? So first of all, once you understand this, what I have actually asked is that beta is the vector 1, 1, right?
Yes.
Gamma is the vector 2, 3. Remember, the lattices go from beta I, gamma I to alpha I, delta I.
Yes, ma'am.
So these are my beta I's, these are my gamma I's, these are my alpha I's, and these are my delta I's. So with this notation, what I am actually saying is that beta is my 1, 1, gamma is 2, 3, alpha is 2, 3, and delta is 1, 0. And now for this, the possible lattices, if I draw out the non-intersecting ones, because that is what I'm dealing with, you have the lattice, this choice is there, or this choice is there, okay, which is here. So if let's say I take this choice, then there is exactly one possible choice for the other lattice, which is non-intersecting from this, right?
Yes.
Which is exactly this. The other choice for the first lattice was this. Now, once you have taken this to be the first lattice and you start here, you cannot go down because you will intersect. So you have to go up, where that is certain. Now, when you are here, you could either go down or you could go right. So here I have taken a right and here I have taken a down. So if I take a right, you cannot go further right because then this point would be missed. Okay, so you have to go down, down, down. No other possibility. Here I had taken a down here. So now can I take a down now? No. This will get intersecting with this. I have to keep it non-intersecting. So I take a right. After you took a right, then there is no possibility left. You have to take a down, down. So these are the only possible non-intersecting N2 paths of type alpha, beta, gamma, delta, where alpha, beta, gamma, delta are these, right?
Yes.
Now with this entire notation in place, whatever we have talked about, you take all these products and then you take their summations. What happens is, what is the horizontal weight of this?
Which one, ma'am?
This one,
X2, right?
x2. Horizontal weight of this lattice,
X3 square.
as in, sorry, weight of this lattice is x3 square, weight of this lattice is x2. So weight of this two path is x2, x3 square.
Yes.
Now you come to the next lattice. This is, what is the horizontal, what is the weight of this lattice?
X2, X1.
And weight of this lattice?
X3 square.
X3 squared.
So weight of this entire two path is?
X1 times X3 squared.
And for this end path is?
The one is X1
Yeah,
and the other is X2, X3.
right. So that is going to be x1, x2, x3. And then you have to sum them up, right? Beta be the sum of their weights. So you sum their weights and it's going to be x2, x3 square plus x1, x3 square plus x1, x2, x3. So one thing which you should notice here is that whenever you're dealing with such a scenario, this, what is left at the end is a monomial polynomial. As in, what is the correct word? So cumulative power of each of the terms remains same.
The degree.
Degree, right. It's a homogeneous, not homogeneous. It's a polynomial, multivariable polynomial of a fixed degree.
Yes.
Okay. So yeah, I mean, and if you have seen determinants in other contexts, you would know that they are given by symmetric functions of certain type.
Yes, ma'am.
So in contrast to that also, you can read this up, but that is not part of this syllabus. So we'll not touch that. I just wanted to show this to you people so that if at all you are interested, you can go back and read more on it and satisfy yourself that these things do occur in many contexts. So yeah, tomorrow we'll meet again for the next lecture and we'll start new topic. You people saw I have uploaded the PDF of book.
Yes, ma'am.
Okay.
Yeah, the next chapters are easy, right?
That's right.
Yeah.
Yeah. Okay, so I'll announce the quiz on Moodle now. And then, yeah, syllabus will be up till tomorrow's lecture.
Okay, ma'am.
Okay. Okay. See you. Bye.
Bye, ma'am.